This is part 2 of the lecture on the Michelson-Morley experiment. Now what we do is we develop the mathematics behind the experiment. As we do, we're going to begin to see the basic equations of special relativity. That is, they're going to begin to come out. Okay, now first of all, we have to define some things here. Notice that I still have here on the board, I have the diagram from the end of the previous video. Once again, we consider the ether to be this universal reference frame, consider that to be this classroom, consider it here to be the board. Okay, the reference frame that is stationary, the ether, if you recall from Galilean relativity, we always refer to as O. So O is the ether. Okay, and then we have the moving reference frame. The moving reference frame is the interferometer itself attached to the Earth, and it then moves with respect to the ether with the velocity u that I indicated earlier. So O prime is the Earth with the interferometer attached. Okay, and then the object in all of this is going to be the light. And then what we're going to do is we're going to calculate the amount of time necessary for the two beams of light to complete their paths. We first of all have what we're going to refer to as T sub A. This is going to be the time necessary for the light to move along what is called the perpendicular arm. That is, the light beams go out, it hits the mirror, and then it comes back. After that, we're going to calculate then the time necessary for the light beam to go in the downstream and upstream direction for mirror B. That would then look something like this. The time to go downstream plus the time to go upstream. We're going to compare then T sub A and T sub B. We will find that they are not quite the same thing. In order to calculate those times, we're going to use our old friend, the Galilean transformation, back from the first semester. That is this expression here. R equals R prime plus UT. Okay, now here are what those vectors mean in this context. So first of all, R. That's going to be the position of the object, the light, with respect to the stationary reference frame, ether. R prime is going to be the position of the object, the light, with respect to the interferometer, with respect to the Earth. And then the UT, this right here is going to be the position of O prime, the Earth with the interferometer attached to it, with respect to O, with respect to the ether. Okay, we also have to continue here with some definitions as well before I begin. Okay, the arms of the interferometer, as I indicated earlier, have the same size, the same distance, that is. This distance here and this distance here, that distance is always referred to as L. Okay, now let's go ahead and calculate what's referred to as T sub A. T sub A is the time necessary for the light to move along the perpendicular arm and then return to its original location. In order to do so, I have to do some erasing here on the board. Okay, so now draw this portion here of the diagram from earlier, and then we have the following sequence of events. Okay, first of all, the light leaves the source, and then it hits the mirror. It hits the mirror, for example, when the mirror is over here. Remember that once again, we're assuming that the Earth, with the interferometer attached to it, is moving in that direction relative to the ether. Okay, and then the light reflects off the mirror, and it then returns to the source. Like so. So the interferometer is here like so, when the light then returns to the source. What I'm going to do is take this diagram, which is basically nothing more than the following. The light beam goes out, hits the mirror, and then comes back to the source. What I'm going to do is take this diagram and I'm going to split it up into two. We're going to divide it in half, that is, to create right here, for example, a right triangle. Okay, and now the sides of the right triangle are the different vectors in the Galilean transformation equation. Once again, R equals R prime plus UT. So which is which? Well, first of all, right here is the arm of the interferometer itself, and remember that this is referred to from earlier as L. That's the position of the light relative to the Earth, relative to the interferometer. Relative to the interferometer, the light just goes from here to here. L is R prime. Okay, now this side of the triangle here, this right here is UT. This is the position of the Earth relative to the ether in 1/2 of the time that we're going to calculate. So this distance right here, UT, we're going to write as U times T sub A over 2. Okay, and then lastly, we have the hypotenuse of this right triangle. The hypotenuse of the right triangle is the position of the light relative to the ether. Relative to the ether, the light goes from here to here. This right here is the vector R. So then therefore we have here UT plus R prime is equal to R on the diagram. Now what is that distance R equal to? It's equal to the speed of light multiplied by this time, T sub A over 2. When the speed of light was first accurately measured back in the mid-19th century, it was just assumed that what they were measuring was the speed of the light relative to the ether. So then therefore, if this is the position of the light relative to the ether, this is equal to the speed of light c multiplied by the time of T sub A over 2. And now all that I'm going to use here is Pythagorean theorem, and then use Pythagorean theorem to solve for T sub A. So let's go ahead and do that. Okay, so using Pythagorean theorem, I have now u squared T sub A squared over 4 plus L squared is equal to the hypotenuse squared, like so. And then as I said, let's just now go ahead and solve for T sub A. So to solve for T sub A, I'm going to take this term here and then subtract it to the other side like this. Like so. Okay, I'm going to go ahead and factor out now a couple of things from this. I'm going to go ahead and factor out on the right-hand side T sub A squared over 4 from each term. Like so. Okay, and then let's go ahead and cross multiply the 4 here to the other side, and then take the parentheses and place it down in the denominator on the other side to now get T sub A squared by itself. So T sub A squared is then therefore going to be the following. Like so. And now before I do the last step here, which is just going to be to take the square root of both sides, what I'm going to do is I'm going to do an extra step in the denominator. The reason I do this extra step is because you're going to see a term appear that will pop up in relativity all over the place later on. For now, however, here's how we see this term. What I'm going to do from each term here in the denominator is factor out a c squared from both, such that it looks like this. Like so. So take a look at that carefully. Notice that I factored out a c squared from each term here in the denominator to arrive at this. And now let's go ahead and just take the square root of both sides. When I do, I'm finding T sub A. This is the time necessary for the light to travel along the perpendicular arm. So T sub A then therefore ends up being the following. This expression here. Okay, now what we'll do is we'll repeat the calculation, but in this case it's going to be for mirror B. Mirror B is the parallel arm that is parallel to the direction of motion. We're going to split the calculation up, however, into 2 parts. We're going to calculate, first of all, the time necessary for the light to go downstream. We're going to call that time T1. And then we're going to calculate the time necessary for the light to go upstream. We're going to calculate that as T2. We'll add the 2 together to get then what is referred to as T sub B. Once we do, we'll compare it to this value here. Okay, let me go ahead and do some erasing. Okay, so now this calculation is going to be for T sub B, but as I said, I'm going to split it up into 2 parts. So we're going to calculate, first of all, time T1, we're going to call it. This is the time necessary for the light to go downstream. Think of this, by the way, as being analogous to a current of water, and consider the light to be a boat or a swimmer. So then therefore, let's calculate the time necessary for the light to go downstream in the direction of the motion of the current, like so. Okay, now, in order to do so, let's draw out the following. Okay, here's this arm of the interferometer, and now let's say specifically that when I have the diagram like this, the light leaves the source. And now remember, by assumption, that the Earth with the interferometer attached to it is moving in this direction with velocity u relative to the ether. So then therefore, when the light hits the mirror, is the mirror still going to be here? No, it's going to have moved downstream. So then therefore, when the light hits the mirror, the interferometer looks like this. I'll use a different color. Like so. So right here now, the light hits the mirror. And then all three of these vectors here are on this diagram. Here are the various vectors. First of all, UT. UT is the position of the interferometer, the Earth, relative to the ether after this time T1. That's this distance right here. In this time T1, the interferometer is moved from here to here. Like so. Okay, now what about R and R prime? First of all, R prime. R prime is the position of the light relative to the Earth, relative to the interferometer. Relative to the interferometer, all that happened was that the light went from here to here. So right here on the diagram is the R prime, which is once again equal to the length of the interferometer L. And then lastly is R, the position of the light relative to the ether. Relative to the ether, the light went from here to here. So right here on the diagram, like so, is the position vector R. Notice how the vectors add together here. We have UT plus R prime is equal to R. Now, once again, the position of the light relative to the ether was assumed to be the speed of light c multiplied by this time of T1. Like so. And now let's just add things up on the diagram. So UT1 plus L is equal to CT1. Like so. And now we just solve for T1. So move this term to the other side to do so. Like so. Factor out a T1 from each term there on the right. Like so. And then divide by the parentheses. Like so. Okay, now we repeat this process to go upstream, and then we calculate the time T2. Basically the same sort of diagram, it's just that a couple of the vectors are switched around. Okay, so now T2. This is the time to go back upstream. And then we begin with the red portion of the diagram here on the top board. Now we'll think of it as the light leaving the mirror. However, when the light returns to the source is not going to be here, because remember that the Earth, with the interferometer attached to it, has moved downstream in this time of T2. So when the light returns to the source, the interferometer, will say, is right here. So the light returns to the source. Okay, and now on this diagram, we once again have our individual vectors. So which vector is which? Well, first of all, right here once again is the UT vector. So this is the distance that the interferometer, the Earth, moves downstream with respect to the ether in this time of T2. So this right here is UT2. Okay, now relative to the interferometer, relative to the Earth, the light goes from here to here. So this right here is the R prime vector. Yes, it's the R prime vector. This is the position of the light relative to the Earth, relative to the interferometer. Once again, it's equal to the length of the interferometer arm L, but notice that it points to the left-hand side of the diagram, hence the negative sign. Okay, and then lastly is R, the position of the light relative to the ether. Relative to the ether, the light just goes from here to here. So right here on the diagram is the position vector R. So notice how things add up by using the tail to tip method of vector addition. R prime plus UT is equal to R. Once again, this is the position of the light relative to the ether. It's equal to the speed of light c relative to the ether multiplied by the time t2. It does point to the left-hand side of the diagram, however, hence the negative sign. And now we just add things up. So R equals R prime plus UT. And now we just solve for that time of T2. So to solve for T2, take these two terms here and then switch them like so in the equation. And then on the right-hand side, factor out the T2 from each term. There we go. And then divide. Like so. So up on the top board is the time to go downstream. Right here is the time to go upstream. And now we add the two together to get the time T sub B. All right, so let me erase all this. Okay, and now the time T sub B is T1 plus T2. So from the top board, we have this, plus here from the bottom board, like so. Like that. Okay, now let's add the two together by getting a common denominator between them. So the common denominator is going to be these guys multiplied together. So then therefore here in this term, I'm going to have L times C plus U. And then for this numerator, I'm going to have L times C minus U. And then I have my common denominator like so. Okay, let's go ahead and simplify this. Okay, so first of all, in the numerator, I have LC plus LC, which is 2LC. But I also have in the numerator LU minus LU, which drops out. And then if you FOIL these guys here in the denominator, you then end up with this. Like so. Okay, now that is the time T sub B, but before I write it over there on the right-hand board and compare it to the earlier time of T sub A, once again, in the denominator here, I'm going to do one extra step. I'm going to factor out here a C squared from each term, such that it looks like this. Like so. And notice that the C cancels. Here and here. So this is the time for the light now to move along the parallel arm. This is T sub B. And that's this expression here. So compare the two expressions to each other. Oops, here's a C. Compare the two expressions to each other. Notice that they're not quite the same thing. Now, because the fraction u squared over c squared is a number that is less than 1, this then means that the time necessary for the light to move along the parallel arm is a little greater than it is for the perpendicular arm. Therefore, when the two beams of light go out from the source and then return to the source, the light beam that moves along the parallel direction takes a little bit more time to arrive back at the source. Therefore, once again, the two beams of light arrive back at the source out of phase. They do not constructively interfere with each other. So instead of seeing a bright fringe, you would then once again see a dark fringe. Once again, this is the theory behind the experiment. Let me conclude this here as part 2 of the lecture. What actually happened in the actual experiment, I'll get to then in part 3.